This is the last lecture of the week 3, and we're going to discuss causality and regression analysis. So in the previous lecture, we said that if the two conditions are satisfied for omitted variable bias, then our OLS estimator, or beta hat 1, will be biased. So this raises a bigger question. What is beta 1? And what are we actually doing when we're estimating beta 1? So what we want to estimate when we run a regression. There are at least 3 possible answers to this question. The first is that we just want to estimate the slope of a line through a scatter plot as a simple summary of the data to which we attach no substantive meaning. In other words, we're just trying to measure the relationship between x and y. This can be useful at times, but it's not very interesting, so this is not what we want to do in this course. So the second answer is that we want to make forecasts or predictions of the value y for an entity not in the data set, for which we know the value of x. So in our policy question, we may want to know the average test score for a school district that we know the student-teacher ratio. So knowing the student-teacher ratio would help you predict what is the potential average test score. This is an important job for economists, and it's possible to make predictions without knowing the causality. The third answer is that we want to estimate the causal effect of x on y. So someone may be interested in what is the impact of reducing the class size by 2 students per class. What is the impact of this on test scores? This is a causal effect question, and this is something that we're interested in. So what is a causal effect? We know that correlation doesn't necessarily imply causation. So in this course, we're going to take causality to mean that it's an effect measured in an ideal randomized controlled experiment. What is an ideal randomized controlled experiment? Ideal meaning that subjects all follow the treatment protocol. So everyone follows a rule. There's a perfect compliance. There's no error in reporting. Randomized meaning that the subjects from the population are randomly assigned to either treatment or control group. And controlled meaning that having a control group allows to measure the effect by looking at the difference in outcome between treatment and control groups. And lastly, experiment, meaning that the treatment is assigned as part of an experiment, that the subjects have no choice to choose which group they want to belong to. Going back to our policy question, if we think about the ideal randomized controlled experiment for measuring the effect of student-teacher ratio on test scores, we would have to randomly assign students to different class sizes. And because students are randomly assigned, all student characteristics, or the UI, would be distributed evenly. So this means that the expected value of UI given STR is equal to 0, which means the least squares assumption number 1 actually holds in a randomized control experiment. So in our case, we cannot randomly assign students to different class sizes. So we don't have the data from ideal randomized control treatment. We actually have observational data. For instance, we have shown in previous lecture that % English learners is one of the omitted variable. It satisfies 2 conditions. % English learner is a determinant of test score, and it's also correlated with student-teacher ratio. In other words, we don't have control and treatment that are randomly assigned. So the correlation of student-teacher ratio and percent of English learners is not equal to 0, violating our least square assumption number 1. So what do we do when there's omitted variable bias? There are 3 different ways of dealing with the omitted variable bias. The first is to run a randomized controlled experiment where you assign students randomly to different class sizes. This should actually make whatever is an error term or what is omitted variable distributed evenly across treatment and control group. But this is rarely feasible. So the next approach that we can take is cross-tabulation approach. In this case, we try to match schools that have the same share or percentage of English learners, and then compare the test score between large and small class. The problem with this approach is that you may not find the exact match. You may not have enough data to have match for each percentage of English learners. The last and the best solution for dealing with omitted variable bias is to include whatever variable that is missing. And you'll have more than one regressor.